for Inference. This is the final review packet. Now remember, you're expected to take notes on the video and then do the problems that are in the packet, and then after that you are going to check your answers, and anything that you get wrong, go ahead and make sure you look at the reasoning behind the answers. This one here we have hypothesis test and confidence intervals, which of course is our phantom and panic. Now remember, all tests assume a simple random sample from the population being studied. You have to be very careful, make sure that you see it's from the population being studied, not just from somewhere else. All tests are testing to see if the sample has enough evidence to claim the populations involved meet the criteria. So to get full credit, when it says null hypothesis, that's the H in my phantoms. So that's my H. Write which test you're using, that's N, name my test. Write and check all conditions, that's A, as per the assumptions. Give a test statistic, which is T, test statistic, and the p-value, so T and the O is obtain the p-value. Reject or fail, so that's making a decision to reject or fail, and then state the conclusion and context. Now, the P, which is not mentioned here, of course you have to use the P when you're using mu, the true mean, or you have, if it's P, the true proportion, or if you're using, of course, mu1, mu2, same thing, p1, p2 would be the same thing, mu d would be the mean difference. Now, if you're using beta for linear regression, it would be the true slope. But this is only, of course, so this isn't a t-test, any of the t-test, any of the z-test. But when you come to the chi-squared, your chi-squared, you're not, the only reason that you have the P for phantoms defining these is because you're using symbols. So whenever you're using symbols, you gotta tell me what the symbols mean. So with the chi-squared, you're actually just writing it out. They are independent, or they're the same, or something like that. So you don't have to do all of the different defining of the labels. Okay, so you either have enough evidence to claim whatever alternative hypothesis represents. Basically, having enough evidence means rejecting Ho, because I'm rejecting Ho to say I have enough evidence for Ha. Or you do not have enough evidence, or you just fail to reject. You never accept, so put this down here, never accept. You never accept Ho, you never, you just are going to reject it or fail to reject it. Okay, so for confidence interval, the acronym is PANIC. So identify the name of the interval, that's the I in panic. Write and check all the conditions. So that's my assumptions and conditions. Correctly calculate the interval. That also goes along with the I to do, and then correctly interpret, PANIC. And then you must interpret the confidence level also. And that is part of my conclusion. So, and then identify, sorry, this should have been N. I don't know why I said. Yeah, you have to correctly identify the interval by name or by formula. So for instance, this here is the 1 prop z interval, and you can call it the 1 prop z interval, or you can use the formula that I just did, or you could put your data in. Let's say p hat equals 1/3 plus or minus, let's say it's 95%, so 1.96 times 1/3 2/3 over, let's say there was a sample size of 300. So any of these would be acceptable. I prefer you either do this one and this one. I like you to do those two. Those are the two that I recommend. If you make some mistake, you forget a hat or something like that, you end up losing credit. So I recommend that you choose the ones that I circled. If you are unsure, just use this one. And then in your, you're going to put it obviously in your calculator, and you will have p hat equals 1/3, z star equals 1.96, n equals 300. With this here, this would be full credit. If you had all of these things here, that would be full credit, of course, then when you also give the interval that it gives you as the lower bound and upper bound on your calculator. Okay, let's talk errors. A type 1 error is alpha, and alpha is, of course, the significance level that we have been using to reject or fail to reject ho. But a type 1 error is when ho is true, but you go ahead with ha. So you've rejected ho and you shouldn't have, and the probability of a type 1 error is alpha. The probability of a type 1 error is alpha because that is the percentage of times that we will actually reject. Type 2 error, the probability of a type 2 error is beta, and that is the opposite when ha is true but you fail to reject it. Type 1 and type 2 error are inverse related, so what that means is type 1 goes up, type 2 goes down. As one increases, the other decreases. But power is 1 minus beta, so as power goes up, or type 1 goes up, power goes up, and type 2 goes down. You will not be required to calculate type 2. You may be required to calculate power given your beta. It will give you a beta. So here we go. The biggest thing with hypothesis and confidence intervals on your calculator, I've given you a grade, on all the tabs, I've given you each hypothesis test on each one. So the biggest thing is identifying it and knowing what the ho and the ha is. So here are some questions that you're going to be asking. Is it categorical and quantitative, and why is that important? Well, if it's categorical, what categorical means is that that's going to be asking questions, do you like the color red? And we're going to get a proportion. And if we get a proportion, that's going to give me a z-test or a chi-squared. Quantitative is going to give me a t-test. And the t-test, of course, is the 1 sample t, 2 sample t, paired t, or linear regression t-test. So those are the different things. And then, of course, you do a hypothesis or an interval as well. So let me jump back here for one more thing, just to kind of remind you what we are actually doing, and then I'll jump back to the test. Remember, on the hypothesis, I just want to reiterate to you what you're doing. If you're doing any of the t-test, it's a normal model where, of course, my center is this. Once I do this, the center is 0 and 1, but really we're making it as 0 and 1 for all of our normal models, which is fine. But really what's happening is mu is my center, and I'm testing my x bar to see if it's significant, to see if it's unusual or not. Now we are standardizing it and making it 0 and 1, where obviously this is 0 and this is 1, 2, whatever, and I'm finding my z-score for my x bar minus my mean divided by my standard deviation. So I'm finding that and converting it to here. But essentially, this is what I'm doing. I have a model that the center is mean, and I'm trying to say, is my sample unusual? Does it have a real low p-value? Which means if the p-value is low, what that means is that my sample is so unusual that that's the percentage of time it could happen by chance. Okay, if I'm doing a p, though, it'd be p and then p hat. It's the same. Again, we're normalizing it where my z is equal to observed minus mean divided by standard deviation. And same thing. And if I'm doing sampling distribution, of course, that'd be square root of n. It just depends on if it's a sampling distribution. Same thing with this one. And then finally with chi-squared, remember it starts here at 0 and my chi-squared statistic is here. Oh, and you would write for t, since it's a t distribution, you put t degrees of freedom here. Same thing with here, chi-squared degrees of freedom here. And then you would name, I don't know why I did normal model. I apologize. That should have not been a normal model. The t is not it's a t distribution. The normal model is only the z, and the chi-squared, of course, is not normal. So the whole thing with the test is the test has a model that is built on the population. And you are testing your sample to see how unusual it is. And if it's unusual, then you're saying that it could, according to my model, basically I need a new model, because according to my model, if the model is true, if HO is true, and that's the definition of p-value, if HO is true, p-value is the percentage of times that this happens by chance. This is a sample of the size that I saw. Okay. Now, conversely, confidence intervals are built, as I already showed you this here, are built on my sample, and I want to know if the population's in the sample. So this would be p hat minus margin of error, p hat plus margin of error, once I do this part here where I showed you the lower bound and the upper bound. And I'm wondering if p is in here. If p is in here, that would be no new evidence. That would be a large p-value. So this would be a fail to reject. But if p is on either side, if p is above or below the interval, that would correlate to a low p-value because it's new evidence. I have new evidence, and this would be a reject. I do have evidence. All right. So remember, confidence interval is built on my sample. So if I had my sample, of course, x bar plus or minus t star, and that's going to be s over square root of n. And that is also based on my sample, and I want to know, is mu in it or out of it? And if it's in it, fail to reject. If it's outside, higher or lower, it is a reject. We have no confidence interval. There's no confidence interval for chi-squared because it is skewed. And remember, the confidence interval is symmetric. It's because I'm the center 95%, centered around my middle. And there's no middle here. This is skewed. I didn't draw it really well, but you're getting the general idea. There you go. All right, so back to the questions. So I just realized that I missed that, so sorry that I jumped back around. So the questions. Categorical is proportion, which is a z-test or a chi-squared test. Quantitative is asking how many people on average like to stay after school, or how many seconds on average do you run the mile. How many samples? Of course, how many samples are taken. If it's a one sample, that would be obviously a one sample T, or a one prop T, Z. Of two would of course be a two sample T, or a paired or T, or a two prop Z. Of course, also, this is with my chi-squared goodness of fit. This is with my two samples here. This would be a chi-squared homogeneity, and this one would be a chi-squared independence, one sample. Are the data independent or dependent? If it's dependent, we have paired. We've got a paired test. All right? We want our things in our RILT to be independent, but sometimes they won't. What exactly are we trying to learn about which populations are trying to make an inference? So that's really important to make sure you read those to see if it has one population or two, right? Because if it has one population, actually, really, let's just go to our two populations. Our two populations is a chi-squared independent, where I'm trying to see, homogeneity, because I'm trying to see if the two populations are the same. I could have a two sample t-test or a two prop z-test. If they're one, everything else is one. What conditions or assumptions? Of course, we're going to talk about those in just a second. But those are generally RILT, is what I've told you, and liner. And let's go through. RILT is random. You always need random. You have to have a random sample or a good representation of a sample. Now, of the representation, you have to have sample or assignment. Now, if it's a random sample and you have no replacement, like, you have 10 people and you are picking one of them for a prize and you take them out, and now you have 9 people left, and that would not be replacement, right? If you have no replacement, you have to implement the 10% rule. for independence. Now, there's nothing wrong with the way I taught you with RILT if you state that they're independent. That's not gonna mess you up. What's gonna mess you up is if you state the 10% rule when you don't need it. And that's what you have to just be careful about. You need the 10% rule only when there's no replacement in random sampling. You don't need the 10% rule if it's a random assignment because you are not intending to replace it anyway. And you are doing a study and you are doing on each particular subject or experimental unit. Large sample, I'm going to go through all the different large sample, but the large sample is the biggest one that has something different for each one. And then the 10% rule, which I talked about just now. And of course, you got to talk about the context. Context, am I talking about cars? Am I talking about weight loss? Am I talking whatever I'm talking about? You have to have that in there. It's free, easy points. Okay, so here we go. Here's a little way to kind of do it. I kind of talked you through it. So for this one, are the data categorical or quantitative? Categorical means proportions. Quantitative means means. How many samples do you have? One sample would bring you to the potential aspect of a 1 prop z-test, a chi-squared goodness of fit test, and a chi-squared test of independence. Let me separate these here. For the 1 prop z-test, you're going to have one sample, one thing, one sample proportion that you're comparing to the population. So literally all the data you'll have in here is p hat equals something, and you'll have p equals something. A chi-squared goodness of fit, chi-squared GOF, you'll have one sample with several categories. And that's where my degrees of freedom is category -1. Okay? So this would be like your M&Ms. So here's an example. You would have M&Ms. And you would have proportion, let's say red, blue, etc. A chi-squared test of independence, you're going to have something that would make sense to fit into that's called a 2x2 table. So you'll have one population, let's say Dawson High School students, and I want to see if GPA, let's say GPA, and after college activities, or after high school activities are independent from each other. So I would say maybe this is going to be, if you had between a 2 and 3, a 3 and a 4, a 4 and a 5, and a 5 or above. High school activities, I may say college, work, or other. And I'd fill this out and see how many people are in each one, and I would put this into my calculator on a chi-squared two-way test is what it's called. Okay, let's go here. If I had a categorical again, and I had two samples, here's my choices. Either a 2 prop z-test, and so in the 2 prop z-test, you're going to have the same thing, except you're going to be comparing two sample proportions to each other. So you'll have a P1 hat, and you'll have that, and that's coming from your sample, and you'll have a P2 hat, and that's coming from your sample. All right? You often will be given a P1 and a P2 with populations, but remember, we're looking, and where my hoe is, that P1 minus P2 equals 0, or P1 equals P2 would be another way to do that. A chi-squared test for homogeneity is similar into the aspect of the independence one because you have a 2x2 table. The difference would be is now, let's say I have Dawson High School and Pearland High School, and let's compare one thing, which was going to be just after, let's put it like this, Dawson High School here and Pearland High School, and let's say after, so college, work, or other. let's just make that 3 columns. And I'm comparing Dawson High School and Pearland High School to say, are they the same? Okay, let's jump back up here now and check out our quantitative. So if it's quantitative, that means I'm asking for averages, for means. If I ask what the average is, here are our choices. Okay, how many samples do we have? We have 1 or 2. Well, if I have 2 samples, that's easy. 2 sample t-test. Well, what that sounds like is that you have 2 separate populations and you have 2 averages that you're comparing. So you have x1 bar and x2 bar. And here, of course, you have mu1 minus mu2 is equal to 0, the same thing in your hoe. All right, so now let's see with one variable, you have either a regular t-test or a paired t-test. So you have to be careful. You have one sample with a paired t-test, but it would look like this. If I was shopping at a store and I wanted to compare Walgreens versus CVS, okay? I'm going to go to these pharmacies. And let's say I get Robitussin at one store and I'm going to see how much it costs. Let's say it costs $4.20 here. At CVS, it costs $5.10, et cetera, et cetera. Let's say I'm going to get some milk because they sell that at the places anyway. And let's say then I'm also going to get some nasal spray or something. Anyway, so I am forced to do things. People would really, really be tempted to call this a 2 sample t-test. But what is paired is the items that I'm doing. If I go to Walgreens and I buy Robitussin, I have to go to CVS and buy the Robitussin. So these are paired data, okay? So that's going to be the hint for a paired t-test. And a regular t-test is where you have one population and you are comparing your sample means to, that says X bar, to your mu. And finally, linear regression t-test, guys, anything that makes sense to put into a scatter plot. And 99.9% of the time, they have data outputs for this already. And so you know that has to be the linear regression t-test. Okay, in a multiple choice, they don't give you all that, but the only thing is so this is going to give me 2 quantitative variables. That's why I have how many variables that make sense to graph. This is the only thing that would make sense to have a scatter plot, a line graph. Okay, let's jump over to the types of tests and let's look at our conditions. So we're going to look at what RILT looks like and what liner looks like in this. Okay, so for a 1 sample proportion here, my hoe is always P1 equals a proportion, and then your ha is P1 is either not equal to, less than, or greater than that same proportion. Now your conditions, that's R, SRS means simple random sample. And so that's my R. And the large enough sample, that's the L, talking about, well, how do I check that? By doing your NP and NQ greater than or equal to 10. So NP, notice it's NP, and NQ greater than or equal to 10. So this is for my test. The interval is a little different because you have to do NP hat, NQ hat greater than or equal to 10. So the interval you have, and this is already included in your calculator for all your notes, but just remember that. Okay, so notice it doesn't have, for 1 sample proportion, you can state each, etc. is independent from the next. That is not going to hurt you ever because you do have to talk about that only with the paired. But you don't want the 10% rule unless if this is an SRS, so the 10% rule, guys, you got to remember, is an SRS that is not replaced. Okay, so the next one, ho is P1 equals P2. Ha, again, same thing, less than, greater than, or not equal to. And there's your SRS again, which is your R. and both from population or a random assignment. Now remember, random assignment, you have to have two things. That's why you don't see a random assignment for the one sample, because what's the purpose of having a random assignment? Means you have two treatments at least, right? So I have to compare them. So that's never going to work in a one sample proportion or a one sample t-test. So that's my R. And then of course my large sample is this. Here's my large, oh, don't want that color. That's here. Large samples here also. And this here. And then you have to do it for both populations though. That's the key here, is that make sure you do both populations. And same one here, N1 P hat, N2 P hat, N1 Q1 hat, N2 Q2 hat. And this is for my integral. Now, on here on the 2 sample, it doesn't say here because this is kind of an old one, but it's actually your PC, because that's the pooled. Don't forget that. Remember, PC is equal to whoops, got it wrong. Is x1 plus x1. Yes, x1 plus x2 over n1 plus n2. So that's your pooled. Now, your calculator gives you that pooled number. It doesn't say PC, it just says P. So it gives it directly to you. And you don't have to write the symbol as long as you write the number. So if you're not sure on the symbols, you definitely can just write, 0.4 times 3 is greater than or equal to 10 or whatever. You can put your data directly in. So these here are PC though. That changed on the CED a couple years ago. All right, so for here, SRS again from the population. Independent. Now this is where the independent comes into play. So independent must be talked about for here. For my, I need each individual to be independent. And so that's why I said it's not going to hurt you to write each one is independent for the next. But this is, as far as what you need it for the means, not for the proportions. So, and then the normal population, that is how you are testing the L. That's the L. And how are you going to do that? With means, remember, it's n greater than 30, or you can graph it. Now remember, if it's not greater than 30, that's why it says or graph. So you're going to do a histogram or a box plot to show that it is approximately normal with no outliers, right? Or here, unimodal symmetric. That's what I'm looking for. For 2 sample, again, here you have your SRS. That's the R of both populations. Notice it says or random assignment. You have to indicate if it's a random assignment or a random sample. When you see when it's 2 sample, I can have a random assignment. I can't have that with 1 sample. It doesn't make any sense. Okay, for the 2 sample, you have to have 2 separate independent populations, and so you need to definitely state that the populations are independent from each other, and that you're going to say that they're normal. How do you show that they're normal? Both graphs are unimodal symmetric, or of course, N1 greater than 30, N2 greater than 30 on both of those. Degrees of freedom, you can use the degrees of freedom here from the calculator. The degrees of freedom for this one is just n-1. You can use n-1 from the smallest n. However, just use this, it's more reliable. Match pairs, the same thing. You have to find the SRS from the population and for the R, and now you have to state that they are dependent, because that's the whole idea. They're paired. They're not independent. And then the population here is normal. The populations, the differences is normal, because remember the way it is if I have before, after, and then this is my differences. So if this is 3 and this is 2, this is 4, and this is 6, 3 minus 2 is 1, this is -2, etc., etc. And remember, I am finding the mean of the differences. This one here is, remember, mean 1 minus mean 2, because mean, if I equal 0, if I solve this by subtracting from the both side, and this is the difference of 2 means. okay? This is the mean of all my differences. So make sure you see the difference of the language. And how do you do that? The same way. It's not any different. Your graphs, differences, unimodal, symmetric, or of course you can use your n greater than 30. Same thing, CLT. Okay, for chi-square goodness of fit, remember it's k minus 1 is your degrees of freedom. And the same thing, you're going to have SRS from the population. The large enough sample to show for L, for large enough sample, for this is you need your expected counts greater than 5. They don't show, I know I've taught you the observed counts are going to be greater than 0 or greater than equal to 1 or whatever, but you got to make sure that they are also counts. You need to make sure you label those. You're given the observed, sometimes you're given more. Go ahead and make sure you do this and put all of the numbers into the chart. And that, because you can't just say expected counts, you would want to just refer to it in the chart that you checked. You need to make sure that you do that as well. Chi-squared homogeneity, this is where I have my degrees of freedom is row minus 1 times column minus 1 is my degrees of freedom. And then you're going to put this in a two-way table and a matrix in your calculator. I do have videos on Canvas that show you how to do this under technology. So look under technology and it shows you how to do every single one of these tests that we're talking about. Independent random counts is the R. The large enough samples, we have 1, again, expected counts. And so this, as you can see, the RILT, you don't have to do as much on this one. This one's SRS from the population and large enough sample. All expected counts are greater than 5, and that's for independence. Does the same way, the two-way matrix also for both of these. Okay, let's look at liner. So for liner, for my R, still independent samples, you can see I have the independent kind of right here, that they're independent random samples, which you can say that for all of these, that they're independent random samples. That is not offensive at all, and you can go ahead and do that. The scatter plot appears to be linear, so this here, there's linear is here, the L is this one here, that's the L. And then the distribution of the values of any given X is normal, and so that's my N, my normal, so that's kind of my large sample size is what we've been doing. And how you're doing that, you're showing the graph of the residual plot. You're going to show, oftentimes I notice that they give you just a dot plot. I don't know if you've noticed that. I've taught you the normal probability, I've taught you a histogram of the residual plot. I've taught you the normal probability plot, which means it has to be straight of the residuals. That's the normal probability plot. That would be the other thing. Guys, you're not going to have to create these. You just have to know how to analyze them. And I do have it on your calculator as well. So that is your N. And then your equal variance. The distributions have the same standard deviations or variances. Variance is equal variance is where that comes from. And that's just, remember that the variability of a point doesn't appear to be changing with X. So this would be, let me just show you, this is a bad one. Let me show you so that's not good, because it kind of looks like a cheerleading megaphone where you're seeing that it's not the same, but you're looking for more even spread, where if it's about an inch above on the top, it's about an inch below on the bottom. Okay. All right, so what I want you to do right now is I want you to, here we go, sorry, here's the note on this. Let me jump to this. If the sample is less than 10% of the population, independence may be a moot point. So you don't have to talk about independence because you have your 10% rule. So the 10% rule you don't use it all the time. That's why it wasn't listed all the time. You have to use the 10% rule though to show independence if of course that we don't have replacement. So this is what I want you to do on this. You are going to read through here, answer all the questions. Is this categorical or quantitative? How many samples do I have? How many variables do I have? And finally, what's procedure? I also want you to go ahead and do the ho and the ha. And then once you know the procedure, you know your ho and ha, then everything else should be fine. There are 20 of them here. You're not to solve them out. You can if you want, of course, and then you can look up the answers by just going to the answers by what's listed here. But what I'm wanting you to do is to do this, and then the answers are on College Board, or excuse me, not College Board, but Canvas, and then you're from there, after that, please go ahead and refer to anything that you are confused with and offer me any questions. And thank you for being patient with me. All right, you guys have a wonderful day.